In this lecture, we're going to go ahead and continue to build upon our circuit analysis skills as they relate to sinusoids. So before we first looked at how to take sinusoid signals and make them into phasors, we learned how to take our circuit elements and represent them as phasors. And in this lecture, we're going to learn how to take our series and parallel impedances and combine them into equivalent impedances. And as we'll see, it's actually really easy. When we're working with phasors, we get to treat everything like it's a resistor. So it's pretty simple, pretty easy to remember. So we're going to go through those, talk about series equivalent impedances, talk about parallel equivalent impedances. We'll also mention voltage division and current division, which will be exactly the same as in your Circuits 1 class. And then we'll work a quick, easy example that shows how this gets put together. So let's just get right into it. All right, so let's first take a look at combining series impedances. So let's go ahead and draw a quick little circuit diagram. Say we've got two nodes, A and B. And you have to forgive my terrible drawing, but imagine that we have an impedance Z1, an impedance Z2, an impedance Z3, let's say all the way out to an impedance Zn, so any sort of arbitrary number of impedances, and they're all connected back here to this node, Z sub n. If we wanted to take this and convert it to an equivalent impedance, where we just had A, so let's call it Z EQ, and then connect it to B. It's just like you learned for resistors. So ZEQ is just going to be equal to the sum of these impedances. So it'd be Z1 plus Z2 plus Z3 plus all the way out to plus Zn. Like I said, exactly the same as you're used to working with resistors. So once you get those inductors, capacitors converted into phasors, everything acts like a resistance when it comes to equivalent impedances in series. One other thing to look at is if we're wanting to sort of consider the voltage on a certain place. Let's say that we wanted to pick one of these impedances and say we wanted to find like V sub I around this one. If we had a voltage source at A and B, we could say that the voltage, VI, and it's just exactly the same as the resistive voltage divider. So it's Vs times the impedance that you're looking at. So we'll call that Zi. That would be this guy in this case, Z sub I, over that equivalent resistance, Z EQ. And that's it. That's all there is to it for finding or combining impedances in series and then doing that resistive voltage divider. As we see, phasors make it super easy. We basically just treat everything the way we treated resistors. Parallel impedances are exactly the same way. So let's say that we've got, again, two nodes. Let's call them A and B. But this time, instead of being in series, we got Z1. Our guys here are hooked up in parallel. Call it Z2. Z3, and again, all the way out to some impedance, Z sub n. Now, if we want to take all of that and combine that into the same deal, an equivalent impedance, so let's have A and B, and we want to drop that down to just being ZEQ. And that's going to be exactly the same as it was for resistors. Remember, it's that inverse 1 over Z EQ is equal to the sum of the reciprocals. 1 over plus Z1, 1 over Z2 plus 1 over Z3, plus all the way out to 1 over Zn. And again, that's all there is to it for parallel impedances. Now finally, if we're doing current division, let's say that we've got some current, let's call it, I sub s, and we want to know the current going through this node. Let's call it I sub I. Then the equation again is the same current division equation as before. So we say I sub I is equal to ZEQ over Z sub I times that source. So there's our equation for current division. So just kind of recap real quick. Let's do that. Let's do it in a different color. Let's do it in green. So if we say series impedance, ZEQ is just equal to the sum of I equals 1 to n of those impedances. And parallel impedance is the same deal. 1 over ZEQ is equal to 1 over, not quite, is equal to the sum I equals 1 to n of 1 over Z sub I. So there we go. There's the concept. Super simple, same as resistors in your Circuits 1 class. So let's go on to the next video and take a look at an example of doing some calculations with some real circuit values. So this example starts off by giving us a current source of I sub S, and then in parallel here we have a 10 ohm resistor, and then a 6 ohm resistor in series with a 40 microhenry inductor, and then a 1 microfarad capacitor. Part A asks us to find the frequency domain circuit. So basically convert everything here into phasors. So we'll go ahead and we'll have I sub S. This will become phasor V. We'll call this one Z sub R1. Here let's have Z sub R2, then just Z sub L and Z sub C. And when we go to combine these as equivalents, we'll refer to these as Z1, Z2, and Z3. So let's start by doing some of the easy stuff. We're given, actually in the expression, I forgot one last thing, and that is that our I sub S of t is given to us as 8 times the cosine of 200,000 radians per second t with no phase angle, and that's given to us in amps. So the first thing that's pretty easy to find is our phasor for our current source. Big I sub S is just going to be equal to 8 at 0 degrees amps. And let's go ahead and use the rectangular forms since we need to use these for calculations. This one's pretty easy. Cosine of 0 degrees is 1, sine of 0 degrees is 0, so this one is actually just going to be 8 amps as a phasor. So that's pretty easy. Let's do the resistors now. ZR1 is pretty easy. That's just, remember, 10 ohms. And let's have ZR2, and that's equal to 6 ohms. Now the next ones are slightly more complex, but not much. ZL, remember our equation for ZL is just J times omega L. So that's going to be J times 200,000 times L, which is 40, times 10 to the negative 6. So punch that into your calculator, and you're going to get then it's equal to, oh, what was it? J8. And then finally, our C capacitance for our capacitor there, so Z sub C. Remember, that's equal to J, let me keep my colors straight, J times -1 over omega C. So dropping that in is going to give us J -1 over 200,000 times 1 times 10 to the -6. And if you punch that in your calculator, you're going to get that it's equal to minus J times 5 ohms. So there we go. Let's go ahead and redraw our circuit real quick as best as we can. Let's see, that's going to be our current source. That's not Z, but I. S equals 8 amps. Starts off by being in parallel. We'll still use the symbols here, but that's just, what, 10 ohms? Then 6 ohms. Then our inductor, that is J8 ohms. And finally there our capacitor, that is minus J 5 ohms. Alright, so there we go. There is our frequency domain equivalent circuit here. Now, part B asks us to find what's called the equivalent admittance. So what is that? Part B wants us to find what they call admittance, YEQ. And that's going to be the equivalent admittance. Let's draw it real quick. It's going to be the one in parallel with our current source. So YEQ. And the reason we use admittance here is because it's actually pretty easy to deal with admittance when it comes to parallel circuits. We haven't really talked about it, but YEQ is just equal to 1 over ZEQ. So if we were to do it the normal way, calculating with impedances, remember we'd have to do that, ZEQ is equal to 1 over 10 ohms plus 1 over, with a sum here, 6 ohms plus J8 ohms plus 1 over negative J5 ohms. Right? Do a bunch of, common denominator stuff. Basically just arithmetic that we don't want to deal with. We can actually cheat a little bit since we're working with phasors. Phasors are awesome. They make everything so much easier. We can cheat a little bit and just use this admittance to get our equivalent thing and then flip it over there at the end. So let's go ahead and do that. We know that our YEQ is going to be equal to Y1 plus Y2 plus Y3. Let's calculate these one at a time. Remember that we had labeled, let's go ahead and put it back up here. So if this is Z1, Z2, and Z3, we're just going to flip them over. So we'll first have that Y1 is just equal to 1 over Z1, which is equal to 1 over 10 ohms. So that's just going to be 0.1 S. Remember, the unit of admittance is Siemens. Now let's do Y sub 2. That'll be slightly more interesting. Y sub 2 is 1 over Z sub 2, and that's going to be equal 1 over, what do we have? 6 plus J8 omega. So we need to do a little bit of arithmetic here. So that's 1 over 6 plus J8 omega. Remember, we're going to multiply by the complex conjugate, 6 minus J8 omega over 6 minus J8 omega. That means that our y sub 2 is just going to be equal to 6 minus j8 omega over 6 squared plus 8 squared, which actually comes out to 6 minus j8 omega over 100. So our final answer there for y2 is just going to be 0.06 minus j 0.08. Oop, not ohms, but Siemens. All right. So that's y2, y3 is equal to 1 over z3. Now this one gets kind of weird since it was that negative j business. We can quickly make a note here that y for a capacitor is just equal to j omega c. So let's go ahead and calculate that one directly. That'll be y3 is equal to j times 200,000 times the capacitance, which was 1 times 10 to the negative 6. And that's going to, let's put that in our calculator, 200,000 times 1 times 10 to the negative 6 is 0.2. So that's going to be J 0.2 Siemens. So now we're ready to add everything up. So we'll have Y EQ is equal to, what did we have? 0.1 Siemens plus 0.06 minus 0.08 minus J 0.08 Siemens plus J 0.2 Siemens. Let's grab a different color here. We'll say Y, EQ, add them all up, and we're going to get 0.1 plus 0.06. So 0. Whoa, that got weird. 0.16 plus 0.2 minus 0.08, 0.2 minus 0.08, 0.12. So 0.16 plus 0.12 Siemens. That is the part A right there. That's part B. Part C wants us to find, find that V that we'd originally labeled, that's the voltage that's across each of these impedances, right? So the voltage that's in parallel with our current source. Now we already kind of know how to solve for this one. This is going to be, we know that V is equal to I times our Z, in this case our Z equivalent and our I source. So the only thing we need to calculate first is just Z equivalent, which we know is the inverse of the Y equivalent. So Z EQ is equal to 1 over Y EQ, so that's going to be 1 over 0.16 plus J, we'll forget the J up here, J 0.12, which means we'll use that complex conjugate. That'll give us 1 over 0.16 plus J 0.12 times 0.16 minus J 0.12 divided by the same thing, 0.16 minus J 0.12. Alright. So that's going to get us what? ZEQ is equal to, so that's just 1 on top, so 0.16 minus J 0.12 over 0.16 squared plus 0.12 squared. So that's 0.16 squared plus 0.16 squared plus 0.12 squared is just 0.04. So it'll be this guy, 0.16 divided by 0.04 minus J 0.12 over 0.04. And now we're back to our ohms. So we've got now that ZEQ is equal to 0.16 divided by 0.04. So just 4. That's nice. Minus 0.12 divided by 0.04. That's 3, so minus J 3 ohms. So there we go. Let's go ahead and also put it in its phasor form. So that will be what? The square root of 4 squared plus 3 squared and an angle of the inverse tangent of minus 3 over 4. Oh wait, what am I doing? We don't need to do this yet. We don't need the phasor. We just want to do math. Maybe I'll edit that out. All right. Let's see, because that's not the answer. That's the impedance. So we need to do V now is equal to 8 times 4 minus J3 ohms. And that is equal to 32 minus J24. Not ohms, but volts. So there we go. There's the answer I would remember from my notes. So if we take this and convert it into a phasor form, because we'll need you need the phasor in order to find the steady state form, that'll be the square root of 32 squared plus 24 squared at an angle of the inverse tangent of minus 24 over 32. So that'll give us first, let's see, the square root of 32 squared plus 24 squared. Square root of 32 squared plus 24 squared is 40. That's nice and round. At an angle of tan negative 1 of minus 24 over 32 gives us minus 36.86, but let's double check real quick. Our axes, we have a negative y and a positive x. So that means our angle is here, which means that the value that we got actually is correct for what we want. So that's minus 36.87 degrees. And that's in volts. There we go. That's part C. Part D wants us to find the... What does part C want us to find? Oh, the phasor current using current division. So here we go. Part D wants us to find I. Now remember that I, way back at the start of the problem, is the current that's flowing through this resistor inductor in series. So we'll need to do some current division. Remember that I, in this case, is going to be equal to our I source times our ZEQ over our Z at that point. So we'll call that Z2. So let's go ahead and fill in the parameters there. So I is equal to 8 times our equivalent impedance, which was, where are you at? 4 minus J 3 ohms. Over the Z at 2, and that was our, if I remember correctly, 6 ohms plus J 8 ohms. So 6 plus J 8 ohms. And there we go. Let's go ahead and solve. Let's say that's going to give us what? 32. Hey, that's pretty familiar. 32 minus J 24 over 6 plus J 8 ohms. Now we just need to multiply by our complex conjugate there. So we're going to multiply by 6 minus J 8 over 6 minus J 8. And that'll give us some crazy stuff. We got a FOIL on the top side here. That'll be what's 32 times 6 plus 32 times minus J 8 plus minus J 24 times 6 plus minus J 24 times minus J 8. Here's our numerator. Then our denominator is just going to be, what, 6 squared plus 8 squared, which we already know is 100, so that's nice. Let's break down some of these numbers. That's going to get us So let's see, punch it into my calculator and actually just check my notes and see what they are. And it's going to be 192 minus J 256 minus J 144 minus 192 over, you guessed it, 100. Now the 192 and the minus 192 are going to cancel each other out, so we're actually just going to get, let's see, I is equal to minus of 256 plus 144 is 400. We got a J hanging out there, J over 100. So therefore our I, our phasor I, is equal to just minus J4, which in phasor form is going to be just 4 at an angle. Since it's minus J4, that would be minus 90 degrees, since it's just an imaginary component. So let's see, so that's our final answer there. The last thing we need to do, part E, wants us to find our steady state, V of t and I of t, which we can really easily because we have the phasors. So we know that V of t is going to be equal to, what was our phasor for V? 40 at negative 36.87 volts. So that's going to be 40 times the cosine. Remember our omega was 200,000 radians per second, so 200,000 t minus 36.87 degrees, and that's in volts. And finally here, our I sub t is going to be equal to, what was it, 4 times the cosine of 200,000 t at minus 90 degrees. And that's amps. Boom. And there we go. That was a long one. But just to recap real quick, we started with a pretty simple circuit of a current source and then some impedances in series and in parallel. We were first asked to convert everything to frequency domain, so convert everything to phasors. And then we started off by finding the equivalent admittance. Remember, we flipped over the impedance, found the admittance, used that to calculate the voltage in series, the voltage in parallel with our current source by flipping it over to find ZEQ. We also used ZEQ to find a whole bunch of other stuff later on down the road. Found our voltage as a phasor. Then we did current division to find the current flowing through one section of our circuit. A little bit of arithmetic there. That's pretty simple. And finally, we wrap things up by finding the steady state sinusoids for our voltage and our current. There we go. All right, so I know that was a long one, especially that example. It took a long time to get through, but hopefully everything made sense. Hopefully you see that everything is pretty simple. Once you convert everything to a phasor, there's really nothing that's different than converting equivalent resistances. So thanks for sticking with me through that long video. As always, if you have any questions, comments, or concerns, please let me know, and I'll look forward to seeing you guys in the next video where we're going to talk about doing another simplification, but it was called the delta to y simplification. And as we'll see with phasors, makes it super easy, if not a little bit tedious. But look forward to seeing you guys there. Thank you.